Hello, everyone. Welcome back to my channel. I'm your academic coach, Yuhyun. As you can see, I'm going to continue the cramming series for AP Chemistry. So I will continue filming video from Unit 5, and I will finish the whole 9 units this year. I have another big announcement. I just launched the official Discord server for my YouTube channel. I strongly recommend all of you to join my Discord server so you can talk to me directly and ask me questions, AP related questions. I will try to record a short 5 to 10 minute video to explain how to solve those problems, and I will try to answer you guys once a day. I will also try to host some free classes so that I could answer your questions live. So I'm gonna put that link in the description box below. So please join the Discord server if you are a student who's studying for AP exam, or please share that link with your friends, with your classmates who need more resources in studying AP. Now let's get started. Unit 5 of AP Chemistry is kinetics. This is basically the study of reaction rate. And here I have listed all of the important concepts and keywords that you are going to learn in this unit. They include reaction rate, rate law, integrated rate law, three reaction orders, elementary steps, rate determining steps, reaction mechanism, collision model, activation energy, including energy profile, Maxwell-Boltzmann distribution, and KMT, and catalysis. Let's get started from the definition of reaction rate. Reaction rate is basically how fast a chemical reaction occurs, and it's measured by change in the concentration of either reactants or products per unit time. Let's say I'm going to make a grilled cheese sandwich using 2 pieces of bread and 1 piece of cheddar cheese, and it takes me about 5 minutes to make this one grilled cheese. Then there are multiple ways for me to represent how fast I can make this grilled cheese. The most obvious one will be one grilled cheese sandwich over 5 minutes. I could also try to use the consumption of the ingredients to represent how fast I make it. Every time I make one grilled cheese, I consume 1 piece of cheddar cheese. So I could use one cheddar cheese over 5 minutes to represent how fast I am consuming the ingredients, aka how fast I am producing a product. And that's the same as when I use the number of the bread. I could use 2 pieces of bread per 5 minutes to represent how fast I can make this grilled cheese. So basically, all of these three represent how fast I can cook or make a grilled cheese. So they represent the same, even though they have different numbers in numerator one, one, two, but they basically mean the same process. And I can apply that idea to chemical reaction as well. Here you see a decomposition of dinitrogen pentoxide. And on this graph, you will see the concentration of the reactants, concentration of the nitrogen pentoxide over time. And it's a decreasing curve because obviously the reactant decreases over time because it is consumed. And on this graph, if I want to find the change in the concentration of the reactants, the dinitrogen pentoxide, what we will do is we can pick any 2 points on this curve and connect them using a straight line and try to find the slope. Well, but that will be just an approximation. So to make it very accurate, that will be basically finding the slope. That will be basically picking a point and drawing the tangent line and trying to find the slope of the tangent line. So that is the accurate rate of change in the concentration of dinitrogen pentoxide. So that represents how fast the reactant is consumed. And just like how I use the amount of consumption of the bread or cheese to represent how fast I can cook, we can also use how fast I consume the reactant to represent the reaction rate. Here, there's another example. Here's another example of chemical reaction. 2 moles of nitrogen dioxide decomposes into 2 moles of nitrogen monoxide and 1 mole of oxygen. And here on this graph, you will see how the concentration of all three species changes over time. So on the y-axis, it's concentration, x-axis, that's time, and then you will see three curves. Okay, obviously these two curves represent products because they start from zero and increases over time. And since nitrogen monoxide and oxygen has the ratio of molar ratio of 2 to 1, so the blue one up here represents nitrogen monoxide, and the red one down here represents oxygen. And this green curve that decreases over time from its max value must represent nitrogen dioxide, the reactant. And again, we can pick any certain point along these curves and draw the tangent line and try to calculate the rate of change. So, for example, let's say I'm going to pick this point at 220 seconds. Okay. Then on this red curve of oxygen concentration, this will be this would be my tangent line. Okay. And then at the same time, this represents the tangent line on nitrogen monoxide, while this represents the tangent line on the nitrogen dioxide curve. So you notice that how they have different slopes. If you actually do a calculation, then you will find that these two slopes, the slope for nitrogen monoxide and nitrogen dioxide, have the same value. The only difference is this one has positive slope and this one has negative slope, but they will be the same value. Let's say +5 and -5. On the other hand, for oxygen, the slope is much flatter. So that's a positive slope, and that will be only half the value of the slope for the tangent line and nitrogen monoxide. And you can also verify that idea when you look at this table. So this is a concentration table. On the leftmost column represent time, and the three columns on the right represent the concentration of three species. Let me pick any two random time intervals. Let me try to pick, let's say, 0 second and 100 seconds. Okay. Then for this 100 seconds, the change in the concentration of nitrogen dioxide would be minus 0.0035 moles per liters. And for nitrogen monoxide, the change in its concentration is positive 0.0035 moles per liter. So nitrogen dioxide and nitrogen monoxide has the same amount of change in concentration. The only difference is one is negative, the other one is positive. And now, if you look at oxygen, then from 0 to 100 seconds, its change in the concentration would be positive 0.0018 moles per liter. That's exactly a half of the change in the concentration of nitrogen monoxide. So, again, um, all these three values have the ratio of 2 to 2 to 1 as suggested by the coefficient of these three species in the chemical reaction 2 to 1. So, in conclusion, for any given chemical reaction, we can write its reaction in terms of the changing concentration of reactants or products. Let's say we have A moles of species X reacting with B moles of species Y, and they produce C moles of species Z. Then, for reaction rate, we could try to use the product Z to represent it. Change in the concentration of Z over delta T, and we're going to divide it by the coefficient of z, which is c here. Okay, and we're going to do the same for x and y. So here I get change in the concentration of x over t divided by a, change in the concentration of y over t divided by b. But for these two reactants, their change in the concentration um, represents how fast they decrease over time. While for products, it represents how fast they increase over time. So these value is positive, these two values are negative. To represent the speed of a chemical reaction, we always want to use a positive value. That's why we add this extra negative sign for x and y. So eventually it shows as a positive value. So again, all of these three value should add up to should be the same. They should be equal to each other. Now you know how we define reaction rate and how we can measure or calculate the reaction rate. Now let's talk about how we can control the reaction rate. There are four main factors that affect the reaction rate. That includes reactant concentration, temperature, surface area, and catalyst. And you are going to learn how each of them affect reaction rate when it comes to microscopic level. For now, let's just talk about macroscopic behavior. When reactant concentration increases, reaction rate also increases. When temperature increases, reaction rate also increases. For temperature, think of storing food in the fridge. Food spoiling is a chemical reaction, and we want to slow down the reaction. And we do that by lowering the temperature. So, lower temperature means slower reaction, aka higher temperature means faster reaction. And when it comes to surface area, a larger surface area always means faster reaction. Think of it as a physical change of dissolving sugar in water. When you put a whole chunk of sugar in water, it's going to take a while for sugar to fully dissolve in water. But if you make it into but instead of a whole chunk of sugar, if you put sugar powder in water, they will immediately disappear. They will immediately dissolve into water. So even though that's physical change, how it works for chemical change or chemical reaction is similar. Larger surface area guarantees higher reaction rate. The last is catalyst. The way catalyst works for reaction rate is different from the other three factors. But again, when catalyst is present, reaction rate increases by a lot, usually by 10 times or even by 100 times. Now let's look at the first main factor, reactant concentration. So reactant concentration obviously affects the reaction rate, and we want to know how they affect the reaction rate. Um, so we need to learn rate law. It's a mathematical expression that represents how concentration of each reactant affects the overall reaction rate. For example, for a given chemical reaction, of 3 moles of A react with 5 moles of B to produce 2 moles of product C, then we can write the rate law using the concentration of these two reactants A and B. And rate law looks like this. Rate is equal to rate constant K multiplied by concentration of A raised to a power n and concentration of B raised to the power of m. Here, what you need to really remember is n and m might not be equal to the coefficients. So n is not equal to 3 and m is not equal to 5. Well, maybe by coincidence, they will be equal to 3 or they will be equal to 5, but that's very rare. And you cannot just depend on the balanced chemical equation to write the rate law. So rate law for any given chemical equation can only be determined experimentally. So you will have to do experiment multiple times, and every time you need to control all the other variables constant while changing only the concentration of one species different. So all of these are very common mistake that a lot of people make. When it comes to such chemical reaction of 2 moles of nitrogen monoxide reacting with 2 moles of hydrogen, you might write the rate law as rate is equal to K times concentration of NO squared times concentration of H2 squared, just because the coefficients of them are 2 and 2. That's not correct. And here's another example. When 1 mole of nitrogen react with 3 moles of hydrogen, it produces 2 moles of ammonia. This is Haber process. And a lot of people write the rate law as rate is equal to K times N2 times H2 cubed. That's also not correct. Again, we can only determine it experimentally. So these are the table that you will need to find the power N and M for each of the reactant species. So for this reaction, We have three trials or three different experiments. And each time the concentration of nitrogen monoxide or the concentration of the hydrogen is changed. And then it measured the initial rate. So first off, I'm going to write the rate law as rate is equal to K times concentration of NO to the power of N times concentration of H2 to the power of M. We need to find N and M to complete this rate law equation. And there are really easy way to do it. What you're going to do is out of these three experiments, you are going to pick two and compare them. The first one, I want to determine N. That means I want to keep H2, concentration of H2 as constant. Well, then it will be trial 1 and trial 3 because for trial 1 and trial 3, concentration of H2 remains the same. And while concentration of H2 remains the same, concentration of nitrogen monoxide doubles. So here I'm going to write 2. Then I'm going to compare how the initial rate changes from trial 1 to trial 3. From 1.23 to 4.92, it has quadrupled. Okay. And now what I'm going to do is I'm going to pick these two numbers. So in place of NO, I'm going to put 2. 2 to the power of N is equal to 4. Then obviously N is equal to 2. That's how I find um, the power of concentration of NO. Now let's do the same for concentration of H2. For H2, I want to make sure that concentration of nitrogen monoxide remains the same. So out of these three trials, then I'm going to pick trial 1 and trial 2. Because for trial 1 and trial 2, NO concentration of NO remains the same. And concentration of H2 doubles, and the initial rate also doubles. So again, I'm going to replace H2 with 2 right here. So 2 to the power of M is equal to 2. This 2 represents how much the initial rate increases. Then I get that M is equal to 1. So eventually I can write the rate law as rate is equal to rate constant K multiplied by concentration of NO to the power of 2 times concentration of H2 to the power of 1. And I can also try to find the K, the rate constant here. And that would be by plugging in the numbers for concentration of NO, concentration of H2, and initial rate. So, for example, I can plug in the numbers for experiment 1. Then it will be 1.23 times 10 to the power of negative 3 molar is equal to K times 0.1 molar squared times 0.1 molar. And then you can figure out the number for K. Okay. Whatever that number is, we need to pay attention to the unit. So rate has the unit of molar. And here, nitrogen monoxide has the unit of molar, and then we squared it. And H2 has the concentration of H2 has the unit of molar. That means eventually the unit for the rate constant K will be molar M to the power of negative 2. Or we could write this as seconds squared per mole squared. Here is another more complicated example. Here we have another chemical reaction where 1 mole of bromide ion reacts with 5 moles of bromide ions with 6 moles of protons to produce 3 moles of bromine and 3 moles of water. And there are 4 experiments in total. So again, first off, I'm going to write the basic rate law. The rate law states that rate for this chemical reaction would be K multiplied by concentration of bromate to the power of N times concentration of bromide to the power of, let's say, M, multiplied by concentration of the protons to the power of L. And now I want to find K, N, M, and L. So let's start from N. To figure out the power of the bromide, then we need to make sure the other two species remain constant. So out of these four experiments, I need to find two experiments where the concentration for bromide and protons remain the same. And that would be experiment 1 and 2. So if you look at experiment 1 and 2, they remain the same. Bromide concentration remains the same, proton concentration remains the same, while the concentration for bromate doubles. And the concentration and the initial rate from experiment 1 to 2 also doubled from 8 times 10 to the negative 4 to 1.6 times 10 to the negative 3. So again, I'm going to plug in this 2 right here. Then 2 to the power of n is equal to 2. This to represent how much the initial rate has changed from experiment 1 to 2. Then I get that n is equal to 1. And I'm going to do the same for bromide. So to figure out M, I need to make sure bromate and protons remain the same. And that would be experiment 2 and 3. For experiment 2 and 3, bromate remains the same. Protons concentration remain the same. And bromide concentration doubles, while its initial rate also doubles. Then this time, I'm going to plug this 2 into bromide, concentration of bromide. 2 to the power of m is equal to 2. M is equal to 1. And the last one would be L, which is for protons. And this time, I need to make sure that bromide and bromate concentration remain the same. So I'm going to pick experiment 1 and 4. So for 1 and 4, bromate remains the same, bromide remains the same, and initial concentration of protons double. And this time, the initial rate actually quadruples from 8 times 10 to the negative 4 to 3.2 times 10 to the negative 3. So I'm going to plug this 2 in to the position of the protons. So 2 to the power of L is equal to 4. 4 is how much the initial rate changes from experiment 1 to 4. Then L is equal to 2. So eventually, I can write this rate law as rate is equal to K times concentration of bromate to the power of 1 times concentration of the bromide to the power of 1 times concentration of the protons to the power of 1. And again, I can find K by picking any one from these four experiments and by plugging in the initial concentration of each species and the initial rate. And when it comes to the unit of the rate constant K, again, we only need to compare the unit. The unit for the rate is molar. Okay. And the unit for the bromide to the power 1 is molar. The unit of the concentration of the bromide to the power 1 is molar. The proton has concentration of molar. So eventually you will see that molar is equal to unit of K times molar squared. That means K will have the unit of molar to the power of negative 2. And we could also write this as seconds squared per mole squared. So you see that how we can experimentally determine the power of the concentration of each of the reactants. And we call those powers reaction order. And the three most common reaction orders in rate law would be zero order, first order and second order. So third order is also possible, but it's very, very, very rare. So here in AP Chemistry, we will only focus on zeros order, first order, and second order. The sum of all those powers of the reaction concentration in the rate law is the overall order of the reaction. But usually, when we refer to zeros order, first order, second order, we are referring to one specific reactant. So, for example, here you will see a chemical reaction that 2 moles of A reacts with 4 moles of B and 3 moles of C to produce 1 mole of D. And let's say experimentally we determine that its rate is equal to K times A squared times B. Then the overall order of this chemical reaction would be 2 plus 1, which is 3. But we rarely say that this order is the third order. Usually, how we talk about it is we say that, oh, this chemical reaction is of second order of A and the first order of B and zeroth order of C. You might wonder why zeroth order of C, because C does not even occur in the rate law. So, since the rate law does not have C involved, that basically means the concentration of C does not affect the rate at all. That means it's concentration of C to the power of Z. So that's why we refer to this chemical reaction as zeroth order of the reactant C. So reaction order is really important because later you will see that in reaction mechanism, it plays a really important role. The problem is it's pretty challenging to find reaction order. We have to perform experiment multiple times by changing different reactant concentration. And if there are multiple species for reactants, then we need to perform the experiments many, many times. And it's time consuming. So that's why we created something called integrated rate law. So by using integrated rate law, then you need to perform experiment only one time, and still you can figure out the reaction order for that specific species. And now think about it. For rate law, it does not really tell us too much information. Rate law is basically rate is equal to a constant multiplied by the concentration of the reactant. So if we represent that in terms of graph, that will be reaction rate versus concentration of species A, or let's say reaction rate versus concentration of species B. This is how it looks. But most of the time, what we care about is how much time it takes to complete the reaction, or let's say complete the reaction by 90%. That's what we usually care about when it comes to reaction rate of any chemical reaction. So we want to see how concentration changes over time. It makes a lot more sense for us to measure that over time as well. So here are the graphs that shows how concentration of any reactant changes over time. And they represent the zeros order, the first order, and second order. So now you see that for zeros order, it's very obvious because it's a linear line. It decreases at at a constant rate. And for first order and second order, they are tricky. So second order has deeper curve, but usually, depending on how you zoom in or zoom out that x-axis and y-axis, it's almost impossible for us to visually determine if that curve represents first order or second order. So let's say you have performed an experiment using a specific concentration of reactants and you measured how the concentration changes over time. I want to know how I can immediately determine the reaction order of this concentration without performing second or third experiment. Then we are going to convert this concentration versus time graph into something else. So we are going to do integration on this function. That will be the integration that you learn in calculus AB or BC. Here, you don't need to know that detailed process of how to do the integration. I will show you in a separate video how that works. For now, you only need to know the corresponding graph. So for zeroth order, it shows a linear decreasing line when you have concentration of the reactant over time. And for first order, it's a curved decreasing line when you draw concentration of the reactant versus time. But if you convert that into ln of concentration of the reactant versus time, then it will show you a linear decreasing line with a slope negative k for first order reaction. For second order reaction, again, that's a curved decreasing function when you plot concentration of A versus time. And this time we can convert it into a linear line by plotting 1 over concentration A versus time. But this time the slope will be a positive k. So, what we are trying to do here is we're trying to do some mathematical manipulation on the y coordinate, on concentration A, to convert these curves into linear line because eventually it's linear line is just very obvious and it's very straightforward. So this means that if you have concentration versus time, and that shows a linear decreasing line, a linear line with negative slope, that means for sure this reaction is of zeroth order for this reactant A. And let's say for this chemical reaction, it shows a curved line when you plot concentration A versus T. But if you plot 1 over concentration versus T, then it shows a linear line with positive slope. Then you can immediately make a conclusion that, oh, that reactant A is of the second order for this reaction. And that's the same for the first order. If it shows a linear line with negative slope, when you plot ln A over T, then it means this is a first order in terms of the reactant A. It's also important that you know how to express these linear lines using linear line function. So obviously, all of you know that y is equal to mx plus b is the general formula for a linear function. So for this zeroth order linear line function, it writes as concentration of A is equal to concentration of A initial. A0 represent the concentration of reactant A when time is equal to 0 minus KT. So again, here negative K represents the slope. And for first order, it writes as ln concentration A is equal to ln concentration A0 minus KT. For the second order reaction, since it has a positive slope, it writes as 1 over concentration A is equal to 1 over concentration A0 plus KT. So it's important for you to be able to draw all of these graphs, and it's important for you to know how to write the linear function for all of these three graphs. So three reaction orders: zeroth order, first order, and second order. And there's something called half life. So it's the amount of time it takes for the reactant concentration to reduce to half. So let's say for decomposition of dinitrogen pentoxide, if you plot the concentration of dinitrogen pentoxide over time, then this is the decreasing curve. So initially, the concentration of dinitrogen pentoxide is zero point 0.1 molar. And after 100 seconds, it decreases to 0.05 molar. After another 100 seconds, its concentration reduces to half again. So this time 0.025. After another 100 seconds, now it's 0.0125. So you see that how that time interval is always consistent. Every time it takes exactly 100 seconds for concentration to halve. So this is a very unique property for first order. So this means that the rate law for the decomposition of dinitrogen pentoxide writes as K times N2O5 to the power of 1 since it's first order. And how we obtain the straight line or linear line function would be by plotting ln N2O5 over time. And it will be uh, a linear line with negative slope k, with negative slope negative k. And usually we use T1/2 to represent it. And T1/2, the half-life, is ln2 over k. And we can easily derive this if you know how to represent the linear line. So we know that ln A is equal to ln A initial minus KT. And now we want to find T1/2, the half-life. After T1/2, the concentration reduces to 1/2 of A initial. So this will be ln 1/2 A0. That's equal to ln A0 minus K T1/2. And if we rewrite this, then K times T1/2 is equal to ln A0 minus ln 1/2 A0. And for log, we can separate it into addition or subtraction. So now it becomes ln A0 minus parenthesis ln 1/2 plus ln A0. So these two cancel out, then we get negative ln 1/2. That will be ln2. So basically, k times T1/2 is ln2. That's how we got T1/2 is ln2 divided by k. And ln2 is approximately 0.693. So this will be eventually the formula that you see on your equation sheet. And again, half-life is constant only for first order reaction. If it's second order or zeroth order, there is also half-life, but every time the half-life will be different. And here there are a few concept check problems for a college board. Question number 1. Here we have a chemical reaction of 2 moles of nitrogen monoxide reacts with 1 mole of oxygen to produce 2 moles of nitrogen dioxide. And the initial concentration for reactants are right here, 0.028 molar and 0.014 molar. The oxidation of nitrogen monoxide producing nitrogen dioxide is represented by the chemical equation shown above. The initial concentration are given. The change in the concentration of nitrogen monoxide, which is the reactant, as a function of time are shown in the following graph. And under the same condition, one of the following graph represents the changes in the concentration of oxygen over the same period of time. Oh, okay. Which graph represent the changes in concentration of oxygen and why? So we know that the coefficient for this balance equation is 2, 2, 1, 2, 2. That means that the rate of change in nitrogen monoxide would be twice as the rate of change in the oxygen. Because by the definition of the rate, we can write this as rate is equal to 1/2 of change in the concentration of NO2 over time. And that's the same as negative 1/2 times change in the concentration of NO over delta T. That's the same as 1 over 1. So basically just negative of change in the concentration of O2 over delta T. So now you see that how NO and O differ by exactly 2 times. So from T is equal to 0 to, let's say, T is equal to around 450 seconds, the change in the concentration of NO is from 0.028, approximately from 0.028 to approximately 0.0002. So that will be around negative negative 0.0026. So if I plug in this value right here, that means 1/2 multiply that would be equal to change in the concentration of O2. So that would that means change in the concentration of O2 within the same period of time should be 1/2 of it, which is negative 0.0013. And that is represented by graph 1. For graph 1, it starts around 0.0014 and then it decreases to 0.0001. So it will be graph 1 for sure. So I'm going to cross out a D, A, and C. And let's take a look at the reason for option A and B. A says graph 1 because the rate of oxygen to consumption because the rate of oxygen consumption is half the rate at which NO was consumed. That's correct. Two molecules of NO react for each molecule of O2 that reacts. That's correct. So A would be the right answer. B, graph 1 because O2 molecule are consumed at a slower rate at the beginning of the reaction when there are not as many molecules of nitrogen dioxide produced. No, so this is irrelevant to the reaction rate. The fact is, they are consumed at the rate of 2 to 1 for nitrogen monoxide and for oxygen. Question number 2. An experiment was conducted to determine the rate law for the reaction. 1 mole of A2 reacts with 1 mole of B to produce 1 mole of A2B. The table above shows the data collected. Based on the data in the table, which statement is correct? And all of the statements mention the rate law. So let's figure out the rate law first off. Rate is equal to K times concentration of A2 to the power of N times concentration of B to the power of M. So out of these 4 trials, first off, let's try to find 2 trials where concentration of B remains the same. I could easily find trial 1 and trial 2 where concentration of B remains the same and concentration of A doubles. And initial rate for trial 1 and 2 doubles. This means 2 to the power of n is equal to 2, so n is equal to 1. Reaction order for A2, species A2 is 1. A2 is first order of this chemical reaction. And then we can compare trials 3 and 4. For trials 3 and 4, concentration of A2 remains the same while concentration of B doubles. And initial rate also doubles from trial 3 to trial 4. So this time, 2 to the power of m is equal to 2, m is equal to 1. This means for this chemical reaction, its overall order is 2, and its first order of A2 and first order of B. So that means B is the right answer, where rate is K times A2 times B. Doubling the concentration of A2 and B will quadruple the rate of the reaction. Question number 3. The initial rates of the reaction represented by the equation shown above were measured for different initial concentration of nitrogen monoxide and chloride. Based on the data given in the table above, which of the following is the rate law expression for the reaction and why? We are given 3 experiment trials. If we compare experiment 1 and 2, then you will see that concentration of NO remains the same, while chlorine concentration of chlorine doubles. And the initial rate from experiment 1 to 2 also doubles. So if the rate law is K times NO to the power of N times Cl2 to the power of M, this means that 2 to the power of M is equal to 2. So M is equal to 1. And now we can compare experiment 1 and 3. Then for chlorine, the concentration remains the same, while the concentration for nitrogen monoxide doubles. And the initial rate from experiment 1, 2, 3 um, actually uh, quadruples. So this means that 2 to the power of n is equal to 4. So n is equal to 2. This means the rate law for this chemical reaction should be K times NO to the power of 2 times Cl2 to the power of 1. So the answer would be D. Question number 4. The reaction represented by the chemical equation shown above occurs in Earth's atmosphere. 2 moles of hydrogen decomposes into 1 mole of hydrogen peroxide and 1 mole of oxygen. In an experiment, concentration of HO2 was monitored over time and the data plotted as shown in the following graph. Based on the information, which of the following is the rate law expression for the reaction? So this is where the reaction order and integrated rate law really matters. Um, when you draw concentration of HO2 over time, it's only going to show you this curved, decreasing curved line, and we cannot determine its reaction order. And this person has converted that into 1 over concentration of HO2 over time. And it shows a positive, a linear line with positive slope. This means that HO2 is of the second order. So the rate law must be rate is equal to K times HO2 squared. So the answer is C. Question number 5. The rate constant K for the decay of the radioactive isotope I-131 is 3.6 times 10 to the negative 3 hours uh, per hours. The slope of which of the following graph is correct for the decay and could be used to confirm the value of K? So, since this is a radioactive isotope, this means that its half life is constant. And when half life is constant, this means that the reaction is the first order of the radioactive isotope I-131. So, this is first order. And for first order chemical reaction, we could make that concentration versus time graph linear by taking the ln of the concentration. So it must be ln concentration of uh, iodine 131 over time. And it should show a negative slope of negative K. So C is the right answer. Question number 6. Hydrogen peroxide decomposes to produce water and oxygen according to the equation above. An experimentally determined graph for the first order decomposition of hydrogen peroxide is provided below. Which of the following best identifies the rate constant K for the reaction based on the information in the plot of ln H2O2 versus time? So first off, it shows a linear line when they plot the ln concentration over time. This means that this reaction is a first order of hydrogen peroxide. And that also means that the slope of this graph would be negative K. That means K is negative of the slope. So C is the right answer. As you can see, if you are very familiar with integrated rate law, it's very, very easy for you to figure out K or the rate law for any given reaction. Now, to understand how the other three affects the reaction rate, we need to understand what's reaction mechanism. Here, I have shown you two different ways to represent how to make a pancake. The first one is chemical reaction, while the second one is reaction mechanism. And the difference between them would be if there is an order sequence of elementary steps or not. For chemical reaction, it's as simple as reactants, arrow, and then products. So a balanced chemical reaction only tells you how much of each of the reactant you need to make that corresponding product, but it does not really show you any details of combining those reactants together. So here for pancake making mechanism, for pancake making reaction, it only shows you the ingredients that you need, but it does not tell you about the temperature. It does not tell you which two to mix together or so. On the other hand, for pancake making mechanism, there are 9 elementary steps in total, and for each step, it makes it very clear which 2 or 3 ingredients you are going to use and what you are going to do to those ingredients to eventually make that amazing pancake. So, in chemistry, each of those elementary steps shows how atoms or ions or molecules interact with each other or collide with each other at the atomic level. And that's really important because that's basically how bonds are broken and formed. And we know that for chemical reaction, that's basically old bonds are broken and new bonds are formed. The problem is all of these bonds formation and bonds breaking do not occur at exactly the same time. So, for example, for this reaction, um, when hydroiodide react with each other to produce hydrogen and iodine, this is how the balance equation looks. And the balance equation makes it look like it's really simple, and this can become these two products immediately. But that's not how it works. If you take a look at their atomic structure, if you take a look at their molecule structure, then you will see that first off, we need to break the bond between two of the hydrogen iodine bond. We need to break this bond and we need to form a new bond between two uh, two iodine atoms. And then we also need to form a new bond between two hydrogen atoms. So you need to break 2 bonds and form 2 new bonds. It's not very likely that all of these 4 actions happen at the same time. So here we introduce elementary steps. And we propose that for this reaction mechanism or for this recipe, it's mostly likely that first off, there is a new bond formed between two iodine atoms, and then this is a transition state. And then now the new bonds between these two occurs, and then the hydrogen and iodine are separated from each other to produce H2 and I2. So there will be 2 steps, 1 step, and then the 2 steps. And how we know if the elementary steps are proposed correctly is by adding them up. The sum of the elementary steps for a given reaction mechanism must be equal to the overall balance equation. So, for example, let's say we have this overall balance equation of nitrogen dioxide reacting with carbon monoxide to produce nitrogen monoxide and carbon dioxide. And this is the proposed elementary steps. And this is step 1, and this is step 2. Okay. Then when we add them up, this is what happens. For the reactant side, we will see 2NO2, 1NO3, and then 1CO. On the product side, I will see 1NO3, 1NO, 1NO2, and 1CO2. Then on the reactant side and product side, I see the NO3 in common, so I can cancel out NO3. I also see one of the NO2 in common, so I'm going to cancel out one of the NO2 on each side. Then eventually I am left with 1 NO2 and 1 CO on the reactant side, and 1 NO and 1 CO2 on the product side. So that means that when I add up these 2 elementary steps, they actually are equal to the overall balance equation. This means that this reaction mechanism might be correct, at least for now. Here's another example. For a given chemical reaction, you can propose multiple reaction mechanisms. For reaction mechanism 1, there are only 2 steps. NO2 plus F2 NO2F plus F, F plus NO2, and NO2F. So to figure out what is the overall chemical reaction, I will try to sum up the elementary steps. This is how it looks when I sum up the two elementary steps. And I'm going to cancel out what I have in common. Then eventually I am left with 2NO2 plus F2 produce 2NO2F. This is the overall balance equation. And now let's take a look at mechanism 2. For reaction mechanism 2, there are 4 elementary steps. And again, I'm going to sum up all of these 4 steps. Again, I'm going to cross out what they have in common on reactant side and on the product side. Then after canceling out everything that I have, then this is the overall balanced chemical equation that I get. 2NO2 plus F2 produce 2NO2F. So now you notice that for both mechanism 1 and 2, they have produced the same overall chemical reaction. This means that both mechanism 1 and 2 might be the right answer, but eventually there will be only one answer. So to figure out which mechanism is correct, we will have to take a look at more into these elementary steps. So, out of all of those elementary steps, we call the slowest one as rate determining step. And now think about making the pizza dough or making a pizza. So, there will be multiple steps here. There are 6 steps. First off, you are going to mix all of the ingredients, including the yeast, with water, and you are going to nicely mix them, make it into dough. And in step 3, what you are doing is you will have to rise the dough, and it takes about 2 to 3 hours. And for all the other steps, it takes as little as 5 to 10 minutes, or even less than that. So eventually, out of all of these 6 steps, what really takes the most amount of time would be step number 3. So how long it takes for me to make the pizza dough really depends on how long it takes for me to complete step 3. That's why we call the slowest elementary step as a rate determining step. And on the right hand side, here is another diagram that can show you why it means by rate determining. So think of each of these passage as elementary steps. So there is like step number 1, step number 2, and it's pretty easy for all of these particles to go through step number 1. And when it comes to step number 2, only these particles was passed through the step number 2 at a very slow rate. So how fast these particles can pass step number 2 really determines the rate or the speed of this chemical reaction. So rate determining step is so important because it controls the overall reaction rate. And what's even more important is rate law of a chemical reaction that we just learned before, that is determined experimentally, is set by the molecularity of rate determining step. And what I mean by a molecularity is we are just going to take the coefficients of those reactants or species, and we are going to put that as the power or the reaction order of that given reactant. So, for example, for this overall chemical reaction of nitrogen dioxide and carbon monoxide, we know that based on the rate law, its rate is equal to K times concentration of nitrogen dioxide to the power of N times concentration of carbon monoxide to the power of M. And we know that N and M does not correspond to the coefficients of this overall chemical reaction. So here the ratio is 1 to 1. But we know that there's no guarantee that N or M is equal to 1. But now we can determine that if we know the reaction mechanism. So this is the reaction mechanism. And step number 1 is slow. Step number 2 is fast. That means step number 1 is the rate determining step. Now let's take a look at the reactant part of this rate determining step. For reactant part, we have 2 moles of nitrogen dioxide reacting together. This suggests that the rate for this total overall chemical reaction would be proportional to concentration of nitrogen dioxide squared. And this square, or number 2, comes from the coefficient of the nitrogen dioxide and rate determining step. This is why the rate determining step is so important. Here I have another example for you. Okay. Now we have 1 fluorine molecule, 1 mole of fluorine reacting with 2 moles of nitrogen dioxide to produce 2 moles of the product. And there are 2 steps. The first step is the slow step. The second step is the fast step. Again, that means the first step is the rate determining step. And that means that for this overall reaction, its rate law can be written as the molecularity of the rate determining step. So it will be K times concentration of NO2 to the power of 1 times concentration of F2 to the power of 1. So here, the power of 1 and the power of 1 follows exactly the coefficients of the NO2 and F2 in rate determining step. So, a valid reaction mechanism needs to meet the following 2 requirements that I just described. One is the sum of all elementary steps must be equal to the overall balanced chemical equation. The second requirement is that the rate law of the slowest step or the rate determining step must be equal to the rate law produced from the experimental experiment. Here I have couples of other questions for you to make sure you fully understood what I just explained. Question number 7. A 2-step reaction mechanism is proposed for a gas phase reaction. Which of the following correctly identifies both the chemical equation for step 1 and the rate law for the overall reaction? So first off, we need to determine the chemical equation for step 1. And that part will be easy because step 1 plus step 2 should give me the overall the overall chemical reaction. This means that step 1 is basically overall minus step 2. So here for overall, I have carbon dioxide on the product side. And for step 2, I also have carbon dioxide on the product side. So that means for step 1, I wouldn't have carbon dioxide on the product side. And for the reactant side, I see that carbon monoxide are there in common for step 2 and overall. So I'm going to cancel that out. So eventually, step 2 can be simplified or cut down to nitrogen trioxide becomes nitrogen dioxide. And the overall gives me nitrogen dioxide becomes nitrogen monoxide. And I only need to subtract step 2 from overall. So how it becomes is, first off, I'm gonna add all of the species that are present in overall to step one. So NO2 on the reactant side and NO on the product side. Okay. And since I'm going to subtract step two from overall, that means that NO3 on the reactant side in step two now goes to the product side of step one. And then NO2 on the product side for step two goes to the reactant side for step one. So this should be how it looks for step one. And this makes sure that NO2 in step one cancels out with NO2 in step two. NO3 in step one cancels out with NO3 in step two. Then eventually you are left with NO2 on the reactant side and NO on the product side. So based on this chemical equation for step one, I could conclude that A is the correct one. 2NO2 produces NO and NO3. And based on that, since step one is the slow step, while step two is fast, step one is rate determining step. So molecularity of step one chemical equation should be the rate law, which is NO2 squared. Next, question number 8. Which of the following represent the overall chemical equation for the reaction and the rate law for elementary step 2? For overall chemical equation, we only need to add up step 1 and step 2. Now I'm going to cancel out what I have in step 1 and step 2 in common. So HI is canceled. And that's and then HCl on the right side, H2 on the left side. Okay. Then for overall, I get H2 plus 2ICl produce 2HCl plus I2. So based on that, I'm going to cross out A and C. So the answer would be either B or D. B and D gives the correct overall reaction. And then now let's take a look at the rate law. For rate law, it aligns with the molecularity of the rate determining step, which is step 1. So the rate law should be K times concentration of H2 to the power of 1 times concentration of ICl to the power of 1. So the correct one should be D. Question number 9. Nitrogen monoxide and oxygen react to form nitrogen dioxide. The rate law of the reaction is rate is equal to KNO squared times O2. If the reaction occurs in a single elementary step, that is a 3-body molecular collision, then which of the following is the equation for the elementary step? So here, it already proposed that there is only one elementary step. Okay, if there is only one elementary step, then that step itself is rate determining step. So that means that this rate law of NO squared times O2 should represent the molecularity of that only elementary step. So it should look like NO plus O2. Then eventually it's 2 times NO plus O2. So B should be the right equation for the elementary step. Question number 10. The particle models shown above represent a proposed two-step mechanism for the destruction of ozone O3 in the upper atmosphere. Based on a proposed mechanism, which of the following is the rate law expression for the destruction of the ozone? So there are two steps, two elementary steps, step 1 and 2. The step 1 is slowest. So step 1 is the rate determining step. So that means that the rate law should align with molecularity of step 1. It should be K times. Okay. Now based on these particle models, we need to write out the chemical equation for step one. It's O3, and this one is Cl. This one is O2. This is ClO. So based on step one, rate is equal to K times concentration of O3 to the power of 1 times concentration of chlorine to the power of 1. So the answer should be C. Oh, my bad. The answer should be D. Next, we need to learn what's collision model to really understand what is going on atomic level when it comes to any chemical reaction. The core idea of collision model is that molecules must collide to react. That means if there's no collision, then there is no reaction. Again, chemical reaction is all about breaking a bond and forming a new bond. And the bonds cannot be broken or new bonds cannot be formed if there's no collision. You need to make sure particles collide with a certain amount of energy. So with that amount of energy, new bonds either form or old bonds are broken. And collision model will explain how all of these four main factors affect reaction rates. First off, you need to understand that even though collisions lead to a reaction, but not every single collision is effective. Not all collisions lead to a chemical reaction. First off, for a reaction to occur, particles must collide with correct orientation. And this is really important. Think about this chemical equation. 1 mole of carbon monoxide reacts with 1 mole of oxygen to produce 1 mole of carbon dioxide and 1 mole of oxygen atom. The product is carbon dioxide, and this is the molecule structure of carbon dioxide. Carbon is in the middle, and then it has bonds. It's bonded to two oxygens on both ends. On the other hand, this is how carbon monoxide looks. So carbon and oxygen are bonded to each other. Now think about it, just using common sense. To add another oxygen to this carbon, then oxygen should be attached to the carbon from the left side. This means that when there is a collision going on between carbon monoxide and oxygen molecule, you need to make sure that it's the carbon side of the carbon monoxide that collides with oxygen molecules. If it's the oxygen side that collides with the oxygen molecule, then there wouldn't be any new bonds forming between these two because we do not need to create, let's say, ozone O3. We want to have a bond between carbon and oxygen, not between oxygen and oxygen. So this is not the correct orientation. So for such orientation, even if it collides very frequently or with a lot of energy, there wouldn't be any reaction going on for that orientation. So the reaction will only occur when the carbon of the carbon monoxide, when carbon side collides with oxygen molecule. For oxygen molecule, it does not really matter if it's the left one or the right one because both of them are oxygen and they're symmetric. So number one requirement for collision model to have effective collision would be correct orientation. And here is another example. We can have ethane, CH2CH2 or C2H4 to react with hydrochloric acid to produce CH3CH2Cl. So again, there could be multiple orientation, but only one of these four orientation will result in a chemical reaction. This is how CH2CH2 or ethane looks. There is a double bond between carbon-carbon atoms, and hydrogen atom is attached to carbon atoms. So each carbon atom is attached to two hydrogen atoms. And we need to make sure that it's the hydrogen that attacks the bond between these two carbon. Because eventually, when CH3CH2Cl is formed, what happens is there would be three hydrogen bonds surrounding that carbon atom. So this hydrogen is the one that's attacking that carbon-carbon double bond. So only this orientation will make sure that there will be new bond forming between this carbon atom and this hydrogen atom. For collision 2, now this is the chlorine side that attacks the double bond. And with such orientation, reaction would not occur. The reaction also doesn't occur if either the chlorine or hydrogen attacks the hydrogen or carbon from the opposite side or the other side. It only happens for a certain orientation. So again, this example shows you that the correct orientation is super important to make sure that collision eventually leads to the chemical reaction. But correct orientation is not the only requirement. Let's say the orientation is perfect, everything is perfect. But if the collision is very, very light and particles or atoms or ions do not collide with each other with enough energy, then eventually the original bonds or the old bonds cannot be broken and new bonds cannot be formed. Then exactly how much of energy is required? That depends on activation energy for that specific chemical reaction. So, activation energy is a threshold energy that must be overcome to produce a chemical reaction. This is how the energy diagram looks. So, on the x axis, that will be the reaction progress. On the y axis, that will be the energy. We call this energy profile of a chemical reaction. So, these are the reactants. Okay. So, for these reactants, it will be two same molecules that consist of three different types of elements. And then this right in the middle is what we call as transition state. And transition state is much higher in terms of energy. And then when it comes to product, the energy drops again because product is usually way more stable than transition state. So higher energy means that less stable, and lower energy means more stable. So we start at a relatively stable reactant state, and then if you want to break the bonds and form new bonds, then you need to overcome at least this much of energy to reach that transition state. And this much of energy is what we call as activation energy, and that is threshold energy. You need a minimum of this much. So again, there are two requirements for a collision to be effective. The first one is correct orientation. The second one is sufficient. Here, I'm going to elaborate on kinetic molecular theory a little bit because it builds that foundation for a collision model. So KMT is a model that uses microscopic behavior of ideal gas particles to explain the macroscopic properties of ideal gases, such as the relationship between pressure and temperature. And there are four really important postulates. Postulate means very strong assumptions. So we're going to assume that these are correct. Number one is these particles are very tiny and they occupy very, very little space, and they're very far away from each other. Number two is these particles are in constant random motion. And what I mean by that here is that they all move at different speed. Some move at very, very small speed, and some has a very large speed. That also means that they move in all different directions. And next, there's barely no attraction or repulsion between particles. Um, we are going to assume that there is no intermolecular forces between these ideal gas particles. Um, so that means every single collision will be elastic. Particles do not lose energy because they collide with each other. The last one is average kinetic energy of these particles is directly proportional to absolute temperature measured in Kelvin. The last one is really important. Since every single particle moves at different speed, they don't have one single speed or kinetic energy in common. Instead, we can measure the average kinetic energy of a sample of gas particles, and that average value is always proportional to the temperature measured in Kelvin. So, based on those four postulates, we can easily conclude that higher temperature leads to higher average kinetic energy. That means, in general, the particles are moving faster. And faster particles mean that the particles hit the wall of the container with stronger force. But it's not just that. It also means that there will be more collision going on in between particles and the wall of the container. So let's say when the particles are slow, they hit the wall at the rate of like 1, 2, 3, 4. But now with faster particles, they're going to hit the wall way more frequently, like 1, 2, 3, 4, 5, 6, 7, 8. And higher frequency of collisions is why the pressure the pressure of these ideal gases are higher when the temperature is higher. So the pressure of gas is the result of the collision, the frequency of collision, not the result of stronger force when particles hit the wall. And these build the foundation for Maxwell-Boltzmann distribution curve. So first off, you need to understand what is a distribution curve. Let's take AP Chemistry as an example. There are 5 different scores that you can get in AP Chemistry exam. And let's say for last year, these many of students scored 1 in AP Chem exam and scored 2. And then the most students scored 3 and 4 and 5. This is what we call as a bar graph or distribution graph for AP exam. So y-axis represents the number of students, while x-axis represents the score that you could get in the AP exam. Now this is nowhere close to this smooth curve, so I can give you another example that looks very similar to that. Okay, now let's take a look at SAT score distribution curve. On the x-axis, that will be SAT score. And let's say the minimum score is 300 and the max score is 1600. The y-axis represents the number of students. Then this is how the score distribution curve looks for SAT. There will be very, very small number of students who score that low. Also, there will be a smaller number of students who score the perfect score 1600. And most of the students will score somewhere in between, let's say 800 or 900. That's what it means by the pick here. The pick does not represent that the score is high. The pick only means that the most common score for SAT would be around 800. And we know that the cutoff line for SAT score is different from school to school. Let's say for this university, its cutoff line is 1400. Will be right here. That means every year only this many students out of seniors are qualified for that university. And let's say that's only 10%. And that idea applies to that idea applies to the collision model. Since these particles go through constant random motion, they have very different speed. So some of the particles have very, very, very small speed that's almost zero, while some of the other particles have very, very, very high speed. And most of the particles will have the speed or kinetic energy that's quite low right here. So this is the most common kinetic energy value that these particles carry. And the activation energy or the threshold is right here. That means only a small percentage or a small fraction of the particles qualify to go through the chemical reaction. Let's say only 5%. And that's how we explain why not every single collision leads to successful chemical reaction. Now let's take a look at how temperature affects this Maxwell-Boltzmann distribution curve and how that actually affects the reaction rate. So when the temperature increases, we know that average kinetic energy of particles in the sample also increases. Okay, then how this distribution curve look would be there are still some particles that carry very small amount of energy, but that number will be significantly lower than the lower temperature. So you notice how at um, at the same energy level, T2 has much fewer particles with that amount of energy, while T1 has much more particles with that little amount of energy. And you also notice that when you move towards the right, when it comes to very high energy, T2, for at T2, at this higher temperature, a lot more particles carry that high energy. Well, for T1, only a very, very, very small portion of particles carry that amount of energy. So when temperature increases, how this distribution curve changes would be first off, its peak will be smaller. Its peak will get lower. So T1's peak is right here. T2's peak is here. The peak gets lower. Number two is the energy level corresponding to the peak shifts towards the right because average kinetic energy increases. So, for example, if there is this temperature called T0 that's even lower temperature compared to T1, then this is how the Maxwell-Boltzmann distribution curve looks for T0. It will have very, very, very high peak, and its peak will occur at very low energy. So, this would be how it looks for T0. What if there's a temperature that's higher than T2? Let's call this temperature T3. Then for T3, it will be lower than T2 and its peak occurs at larger energy. So this is how T3 looks. Again, it's lower than T2 but its peak occurs at a much larger energy. And when you increase the temperature, the shape of these distribution curve changes, while the activation energy itself does not change. And how it helps with reaction rate would be every time you increase the temperature, the percentage of the part or the fraction of the particles that carry sufficient energy increases. Let's say for T1, only this much, let's say only 2% of the particles carry sufficient energy. And for T1, then it's only this much. Let's say that's 5%. For T2, it will be this much. Let's say 10%. And now for T3, this many of the particles carry sufficient energy. And let's say that's 30%. So by increasing temperature, you are just increasing the number of particles that go beyond the threshold. So that meets one of the requirements, which is sufficient energy, and that's how it results in more products in the same amount of time. Last but not least, we need to talk about catalyst. So catalyst definitely speeds up the reaction rate by 10 times or by even 100 times. And how it does it is by providing an alternative chemical pathway for a reaction. Basically, it means it's going to create a shortcut for the chemical reaction. For example, when it comes to the reaction between oxygen molecule and carbon monoxide to produce carbon dioxide, this catalyst, the copper catalyst, will provide a new pathway by attracting the oxygen to itself and by dissociating it to two separate oxygen atoms. And also, it attracts the carbon monoxide. So it's very easy for so it's like pretty easy for carbon monoxide and oxygen atom to combine with each other when both of them are attracted or bonded to the copper catalyst. And by providing that alternative chemical pathway, it significantly lowers the activation energy. So now on this energy profile diagram, you see that how the catalyzed pathway has a much smaller activation energy, while the uncatalyzed one has much larger activation energy. And this is how it looks when you show that to Maxwell-Boltzmann distribution curve. We know that by increasing temperature, the curve itself changes the shape. Catalyst does not do that. It's because it's still the same temperature. It's still the same particles. What it does is it lowers the bar. So now think of it this way. It's the same group of students, and the score distribution for SAT has not changed. But this college will lower the bar this year from, let's say, 1500 to 1400. Then it's going to automatically result in more students who qualify for the college. That's how the reaction rate is increased by using Catalyst. And here is the conclusion. There are four main factors that speeds up the reaction rate. They are reactant concentration, temperature, surface area, and catalyst. And here I'm going to show you one by one how those factor affects the Maxwell-Boltzmann distribution curve. Let's start from reactant concentration. So, what reactant concentration does is it simply just increase the total amount of collision that happens per unit time. So, when reactant concentration increases, there are automatically more number of collisions. It does not change the number, and it does not change the fraction of the collision that leads to effective collision. It does not change the percentage of the correct orientation. The only thing it does is just increasing the total number of collisions. So think of it this way: everything doubles. Everything doubles. And think of it this way. Last year, we had 10,000 students who applied to a college, and only 10% were admitted. And this year, 20,000 students applied to that college, and still 10% of the students were admitted. Well, even though the percentage has not changed, but since the total number of applicants have doubled, so the number of the admitted students will also double. That's how the reactant concentration increases the reaction rate. Next, let's talk about temperature. Again, we know that when temperature increases, average kinetic energy increases, and the Maxwell Boltzmann distribution curve changes like this. So this is low temperature, this is high temperature. At higher temperature, the peak gets lower, but where the peak occurs also shifts towards the right. And this means that when it comes to its right tail, the fraction of the particles that overcome activation energy increases. So originally only this much. So originally, let's say only 5% of the particles have sufficient energy. And now at higher temperature, there are, let's say, 10%. So again, let's say last year, 10,000 applicants, there were 10,000 applicants for a college, and only 5% were admitted. And this year, it's the same number of applicants. But because somehow your school hired a new teacher who teach really well, then everyone kind of scored higher. So this year, 10% of the students pass that cutoff line. That's how increase in temperature increases the reaction rate. And next, it will be the surface area. For surface area, it's basically the same idea for reactant concentration. A larger surface area guarantees more collisions occurring. So again, that's just by increasing the total number of the collisions without changing the percentage or the fraction of the effective collision. And the last one would be catalyst. And catalyst is like cheating. By using catalyst, that means that I'm going to lower the threshold, I'm going to lower my bar. So even though this year the student has not performed better than last year, but just because the college lowers the bar from, let's say, 1500 to 1300, automatically more students, more applicants qualify for that college. And that's how it works for Catalyst. More fraction of the collisions lead to effective collision, or it lead to chemical reaction because activation energy is lowered. Question number 11. The gas phase reaction A2, 1 mole of A2 reacting with 1 mole of B2 to produce 2 moles of AB, is assumed to occur in a single step. Two experiments were done at the same temperature inside rigid containers. Okay, same temperature. The initial partial pressure of A2 and B2 used in experiment 1 were twice the initial temperature initial pressure used in experiment 2. Which statement provides the best comparison of the initial rate of formation of AB in experiments 1 and 2? Okay, so we are going to assume that this occurs in a single step, which means there is one elementary step. And for the only elementary step, that means that its rate law would be molecularity of that only step. So it will be K times concentration of A2 times concentration of B2. So uh, in experiment 1, the partial pressure of A2 and B2 were twice compared to experiment 2. So that means in experiment 1, each of the concentration of A2 and B2 is doubled. That's going to result in quadruple of the initial rate. That's going to result in a quadruple of initial rate for experiment 1 compared to experiment 2. So that means the initial rate of formation of AB is faster in experiment 1. So either C or D. And C says that's because at a higher pressure, the collisions between A2 and B2 molecules would have been more frequent, increasing the probability of a successful collision. D states that because at higher pressure, a larger fraction of A2 and B2 molecule would have the minimum energy required to overcome the activation energy barrier. So again, remember from KMT that pressure is from more frequent collision. And just because you have more collisions does not mean that the percentage or the fraction of the effective collision increases. What it does is it only just increases the total number of collision, just like increasing the total number of applicants for a school. So the right answer will be C. More collision does not increase um, the fraction. Next, question number 12. The proposed rate determining step for a reaction is 2 moles of 2NO2 decomposes into NO3 and NO. The graph above shows the distribution of energies for NO2 molecules at two temperatures, temperature 1 and temperature 2. Based on the graph, which of the following statement best explains why the rates of disappearance of NO2, which is the reactant, are different at temperature 2 and temperature 1? So temperature 2 is higher, temperature 1 is lower. And obviously, since activation energy is fixed right there, that means for temperature 2, there are more percentage. At T2, there will be higher fraction of the particles that carry sufficient energy to make sure the reaction occurs. So, NO2 is consumed at a faster rate at temperature 2 because more molecules possess energy at or above the minimum energy required. Yes, so A is the right answer. A states that um, more fraction of particles has energy that's over activation energy. B states that NO2 is consumed at a faster rate because the molecule have a wider range of energies, allowing for a better orientation. So it's kind of true that it has a wider range of energies, but it has nothing to do with the orientation. So B is not correct. C, fewer NO2 molecules have a relatively high energy at temperature 1. That's correct because at temperature 1, only a smaller portion of the particles have high energy, which favors collisions between molecules rather than between the molecules and the container. So, no, if there are fewer particles with high energy, then it does not favor collisions. The collisions will definitely be um, s- fewer, either between particles or between the particle and the container. So, C is not correct. D. More NO2 molecules have a relatively low energy at temperature 1. That's correct, which increases the number of effective collision taking place. No, it decreases the number of the effective collision taking place. So D is not correct either. Question number 13. Based on a kinetic study of the reaction represented by the equation above, the following mechanism for the reaction is proposed. The equation is 2 moles of hydrobromide reacts with 1 mole of oxygen to produce 1 mole of hydrogen peroxide and 1 mole of bromine. And there are 3 steps: slow, fast, fast. Which of the following rate laws is consistent with a proposed mechanism? Based on the proposed mechanism, the first one is the rate determining step. And the molecularity of rate determining step should represent the rate law. This means the rate law should be proportional to concentration of HBr to the power of 1 times concentration of O2 to the power of 1. So the answer would be C. Next, for the chemical reaction represented above, the following mechanism is proposed. Which of the following initial rate law expression is consistent with this proposed mechanism? Again, step 2 is the rate determining step. So I can easily write the rate law as K times concentration of N2O2 to the power of 1 times the concentration of H2 to the power of 1. The problem is N2O2 is not the reactant. And you notice that for step 1, it's a fast equilibrium. So you see the arrow that's pointing to the right and arrow pointing to the left. Equilibrium means that there is forward reaction and reverse reaction going on at the same time. And this means that the concentration of the products and the reactants for step 1 forms some kind of balance. So this is how it looks for fast equilibrium in step 1. And then I can rewrite the concentration of N2O2 in terms of theater. It will be a constant multiplied by NO squared. Then I'm going to plug this in right here. Then I get K times K1 times NO squared times H2. And K times K1, that's just a constant. So you can write it as K3, K4, or even some other letter. What really matters here is NO2 squared times H2. So the answer would be C. Question number 15. The energy distribution profile curve C for the Y2 molecules is shown in the graph for the reaction. 1 mole of X reacts with 1 mole of Y2 to produce 1 mole of XY2 when it is done under certain experimental condition. Line A represents the most probable energy of Y2 molecules. Line B represents the activation energy. Which of the following changes should be made to the graph to explain the increase in the rate of the reaction if the only change in the experimental condition is the addition of catalyst. So when we add catalyst, we know that it's going to lower the activation energy. Um, but since temperature itself is not changed, so it's the same distribution curve. The only thing it does is it changes the threshold. So we are going to move line B since that was the activation energy. So we're going to move it to the left. So out of A, B, C, D, the right answer would be B. Line B will move to the left because a larger fraction of Y2 molecules will have the minimum energy to overcome the EA barrier. Question number 16. The diagram above illustrates how the reaction N2 plus 3H2 produce 2NH3 occurs on the surface of ruthenium. The rate of this reaction is determined by the amount of energy required to break the bond in N2. This bond is weakened when N2 is observed on ruthenium. Based on this information, which of the following provides the best reason for the use of ruthenium for the synthesis of NH3? So we know that ruthenium is the catalyst here, and catalyst lowers activation energy by providing an alternative pathway. A. It promotes the proper orientation of nitrogen and hydrogen atoms to form new nitrogen hydrogen bonds. B. It provides a reaction path with a lower activation energy. C. It forms a bond between ruthenium and nitrogen that is stronger than the bond in nitrogen molecules. D. It decreases the frequency of collisions between nitrogen and hydrogen. So B is the only answer that relates the function of catalyst to providing an alternate pathway or lowering the activation energy. So B is the answer. That's it for cramming of Unit 5 in AP Chemistry. And again, I will strongly recommend all of you to join my Discord server so you can ask me questions directly. And I will try to answer your question once in a day.